Hello everyone. Last video we talked one example about pure integer programming problem. So sometimes we may have more than one variables are not integers. So we have to, when we finish the simplex method to get the final tableau, we probably need to choose which basic variable we are going to cut off to be integer, right? So in this way here we have two remarks. So first one, if at any stage of the algorithm two or more constraints have fractional right-hand sides, best results are often obtained if the next cut is generated by using the constraint whose right-hand side has the fractional part close to half. Or you generate the cutting plane constraint choosing the largest fractional part in the final tableau. So sometimes we may have a couple of them with the same fractional part. Then you can choose any of them. Now I'm going to give you one more example. So here we are going to talk about another minimization problem. Here I have to say that we use the minimization is not on purpose. I can turn it into maximization as the same, that maximize z prime equals minus x1 plus x2. Okay, we can change it to it. Okay, now we use simplex method to work out the optimal solution for the problem, but without the constraint for variables to be integers. So here when we work out it, you can see the final tableau, x1 and x2 both are basic variables, so they have non-integer values. And here note this 154/4, that is the negative of this z. So z equals negative 15/4 at x1 equals 5/4 and x2 equals 5/2. If you notice this here, you could see that the fractional part of x1 is 1/4. Right? The fractional part of x2 is 1/2. So of course, according to the remarks, we choose the second constraint to cut off, right? And the second constraint, according to the second row, is x2 plus half 1/3 s1 and plus 1/6 s2 equals 5/2. Now, according to that the cutting plane method, and you could see that that's Tij, we give that T21 equals 0 and T22 equals 1, T23 is 1/3 and T24 is 1/6. As the integer part of not just the integer of 1/3 is 0, not just the integer less than 1/6 is also 0, and for xb, not just the integer of less than 5/2 is 2. So in this way, according to the formula on the right, you could see that we can easily to get that G23 equals 1/3 and G24 equals 1/6 and F2 equals half. So in this way, we can easily to write down the cutting plane is minus 1/3 S1 minus 1/6 S2 plus U1 equals 1.5. You probably ask, what if we don't remember this formula? And here has another way to do it, and directly from the constraint. See that second constraint is x2 plus 1/3 s1 plus 1/6 s2 equals 5/2. Now, to cut in the cutting plane, you may simply separate all the constraints and the constant. All the constants, just including constraints and the constant, into their integral and fractional part. As 1/3, you could say that's on, and 1/6, both are fractional part, so you don't need to do anything with it. The constant part, 5/2, you can separate it to be the fractional part as 1/2, and the integral part as 2, right? And what we do next is we simply move all the atoms with fractional parts to the left side of the equation and move all the integer parts to the right side of the equation. So that gives us 1/3 s1 plus 1/6 s2 minus 1/2 equals x2 plus 2. As you could see that we want x2 to be integer. So x2 plus 2 is also integer. So we set a slack variable u1 equals x2 plus 2 for the left and right side of the equation. Then you can see the right side of the equation is also u1, right? Now we just rewrite this equation. Just rearrange, keep that u1 as the basic variable for this equation, which means we keep the coefficients before u1 as positive and move all the variables to the left side of the equation and the constant on the right side of the equation. Then we got minus 1/3 s1 minus 1/6 s2 plus u1 equals -1/2, and that's what the cutting plane equation is, the same, right? So repeat it just directly from the row equation, and then you separate the constants by integral parts and fractional parts. And then you move all those fractional parts to the left and the integral parts to the right. And then set a slack variable equals the right side of those integral parts. And then the right side should be also equal to this slack variable. And then we just rearrange it with all those variables to the left side and constant to the right side. And just remember, we always keep that slack variable with the right 1 coefficient. So in this way, we have the cutting plane equation. Okay. Now, then we bring this cutting plane equation into the final tableau, and it gives us this one. You could see it's a tableau in optimal cases. All the entries in the objective row are positive, non-negative, but u1 equals minus 1/2. So infeasible. Now we use dual simplex method to restore the feasibility. Then we got this result. And from this result, you could see x1, x2 both still basic variables, and x1 equals 3 or 4, x2 equals 2. So you could see that we just cut off the fractional part of x2. However, we still have x1 as a fractional part, so we need to cut the fractional part of x1, and that means we have to continue to work on it. Note that when I work on it, we bring this the cutting plane into the final tableau. I denote it as tableau 2-1. That's the second step, right? So the final tableau for this one is called T22. Okay, now we are going to continue to cut x1, just to make x1 to be integer. That means we will start working on T22. We do not back to the final tableau in the simplex method. Here we are continue to work on it, but it is from that final tableau T22. Okay, now from T22, we are going to work out x1. But when we see this tableau, you could see the fractional part of x1 is 3/4, and the fractional part of s1 is 1/2. And here you may work on x1, just directly work on x1 to just choose that the row 1 to be the first constraint, right? And here I'm going to just continue to use that the column whose FBI is FBI has that fractional parts as half. So here I choose that the third row as the third constraint, right? So here this row gives us equation s1 plus half s2 minus 3u1 equals 3/2. Then we separate those constants, right, as integral part and the fractional part, and now collect those integral parts on the right side and the fractional parts on the left side. That's the simple way we work on. Don't need to remember the equations. And then what we get is half s2 minus half equals 1 minus s1 plus 3u1. And then we set u equals the right side of the equation, 1 minus s1 plus 3u1. Then the right side, half s2 minus half equals u2. So notice that this one is a new slack variable. It's different from u1. Okay, so when we have this, then we get a second cutting plane. Now we are going to bring this second cutting plane into T22 because we got the third row equation from T22. So we bring this second cutting plane back to the T22. Then we get this tableau. And this tableau, the same, you could see that it's in optimal case, but we have u2 equals minus 1/2, so the solution is infeasible. Now use dual simplex method to restore the dual feasibility. Then we get the result. And this tells us the optimal solution is z equals minus 3 at x1 equals 1, x2 equals 2. So we solved the pure integer programming problem. Now we are going to work out the cutting plane method for mixed integer programming. The same method, but we have something special formulas for it. So here we consider this LP problem. We have 3 variables. However, we only need 2 of them to be integers, x1 and x3. But x2, we just need it greater than equal to 0. So if we made this one, we can simply apply simplex method on it. And here is our final tableau. And from the final tableau, we could see that x1 is a non-basic variable, so x1 has a 0 value, and x2, x3 are basic variables. x3 equals 5/2 and x2 equals 19/8. Notice here x2 we don't need it to be integer, so we don't have to worry about it. Here we only need x3 to be integer, right? Because of this problem. So here actually you can use the method we talked for pure integer program problem. You could just simply choose the first row to be the first constraint, and then try to use the cutting plane to cut the fractional parts to make that x3 to be integer, right? Here I'm going to talk another one is you have to use the formula to work on that. So here the general method for the mixed integer programming problem is that if we consider the ith constraint as it appears in the final, like this. So this one, xri, is the basic variable. For this one, for the first constraint in the final tableau, you could see that the first xri should be x3 because we want x3. x3 is the basic variable in the first row, right, in the final tableau, and then we keep the rest, the other variables together, and then equals 5/2. You're going to see this one, right? And then what we do is we have a formula. You just look at it. We have the formula that is, we still use this Tij, Gij, but here the cutting plane equation is defined differently. The cutting plane equation is given by ui equals minus fi plus the dj for all the variables. Here, how to get the dj, it should come from the formula. Okay, now let's. So here, in that final tableau, you could look at that the first constraint, actually you can write it in the equation 2 prime form, that is x3 plus 3/4x1 plus 1/4x4 equals 5/2. Here I have to say that in this final tableau, we denote that as slack variables s1, s2, s3 as x4, x5, x6, just to make them, the order is easy to see. Okay, so here that's the first constraint in our question, right? Okay, now what we do next is we may construct the equation of the current cutting plane by ui equals minus fi plus some of those non-basic variables. Okay, and here we have the largest integer less than Tij plus that fractional part of Tij and equals Tij and x, the same formulas. And here, from here, we could see that because that T11 equals 3/4, so that we have the largest integer is less than 3/4 is 0. The largest integer less than 1/4 is also 0. So in this way, we have G11, G14 the same as T11, T14. And the F1 is the fractional part of 5/2. So that's 1/2. Now, we know G11, G12, F1, but here, this cutting plane actually has nothing. From the formula, you couldn't see it. And how to decide the dj, we have to follow this following formula, dj if Tij greater than or equal to 0 and xj is non-integral, then we choose dj equals Tij. If Tij less than or equal to 0, then we have this formula fi over fi minus 1 Tij to replace by dj. And if xj, we want it to be integral, and then if gij less than equal to fi, then we choose dj equals gij. If xj is what we want to be integer, and then gij is greater than fij, then we use fi over fi minus 1, gij minus 1 to be the value of the dj. Now, in this example, you could see that we already have G11, G14, and F1. You probably say, what about G12, G13? They are zeros, right? So we don't need to consider it. So here, first about D1. D1 relates to the variable x1. So x1 is what we wanted to be integer, right? The problem asks x1 and x3 are integers. So x1 is integer. So in this way, according to the formula about the dj, that we use the last two, right? xj integer, s1 integer. And here we know that G11 is 3 over 4 and F1 is 1 over 2. So G11 is greater than F1. That means we have to use the last formula. Let's say D1 should be equals to F1 over F1 minus 1, G11 minus 1. So F1 half over half minus 1. And G11 is 3 over 4 minus 1. So this D1 equals 1 over 4. And then as x4 is a slack variable, we don't have to have it as integer, right? Because that's a slack variable we add into in the simplex method. So here s4 is a slack variable, maybe not an integer, so maybe it's non-integer. And then we can use the first two formulas to decide the D4, right? So that because T14 is 1 over 4, so in this way we can have it greater than 0. That means we should choose what? The first formula. So that we have D4 equals T14 equals 1 over 4. Then we just bring it into the cutting plane equation that gives us minus F1, that's minus half, plus D1 is 1 over 4 x3 and plus x1, that should be x1, right? x1.